The concept of bond rotation, whether it's allowed as in single-bonded compounds or forbidden as in double-bonded compounds, is a very good entry point into another concept which is of huge importance in organic chemistry. And this is the concept of isomerism. Previously we mentioned that ethane can exist in a number of structures which are related to each other through bond rotation. So this structure, for example, can rotate and give us an alternative but these two structures are clearly the same compound because they're related by bond rotation. But if you look at a molecule with a double bond, and here is an example where we have a double bond and two CH3 groups on the same side of the double bond, and the alternative where the two CH3 groups are on the opposite sides of the double bond, now we know that the rotation around double bond is not allowed, it's rigid. And these two cannot interconvert between each other, so they are different compounds. And again, the reason why they're different compounds is because of forbidden rotation. However, even though they're different compounds, they're clearly similar to each other. In other words, they have the same number of carbon and they have the same number of hydrogens, but they do differ in their bonding arrangements, and they also differ in chemical and physical properties. They have different boiling points and different melting points and many other things. So they're truly different compounds. But to signify this similarity between them, they're called isomers, which simply means that they are compounds with same composition but different structure. Now there are two main kinds of isomers, the so-called constitutional isomers, which differ in bonding sequence, and the stereoisomers, and these two molecules would be stereoisomers, which differ in spatial orientation of the groups. Now let's look at some examples of both of these classes. If we look at the constitutional isomers, for example, molecular formula of C4H10 can indicate this straight chain molecule with 4 carbons, or it can indicate a straight chain of 3 carbons with 1 carbon branch. This in condensed formulas would be CH3, CH2, CH2, CH3, whereas this would be CH3, CH, CH3, CH3. For a molecule with formula C5H12, we can draw a couple of isomers, or the one with 2 branches. And this is an interesting concept. The more carbons we have, the more of these possibilities we have, so the number of isomers increases. I urge you to look at the number of isomers for the molecular formula C5H10. Now this has 2 carbons fewer, 2 hydrogens fewer than C5H12, and these 2 hydrogens can be lost into a cyclic structure, or something with a double bond, or something with 4-membered ring and a branch, and there are a couple of others. And I urge you to find these other isomers. If you want to see an example of stereoisomers, the two that were shown already are of course one of them. This molecule would be called trans-2-butene, and the word trans is important here because it indicates that the two CH3 groups are on the opposite side of the double bond. Its alternative would be the cis-2-butene, which now indicates that the two groups are on the same side of the double bond. And these two are called stereoisomers. Now it's important to note that for the same molecular structures, you can have both stereoisomers and constitutional isomers. So if we have this compound, which has CH2 and then 3 more, this has the same number of carbons and same number of hydrogens as these two compounds. But it doesn't differ only in the orientation space. It differs in bonding sequence as well. So these are constitutional isomers of each other. This concept of isomerism will be mentioned multiple times in organic chemistry. It's probably one of the most important concepts in the structure of organic chemistry. And so we'll come back to this frequently, especially when we actually start studying compounds with double bonds such as these alkenes. But for now, this introduction I think will make you aware of it, and you should practice being able to recognize isomers or possibilities of isomers in pretty much any molecule you see.